use Simpson's rule to estimate this integral from 5 to 8 of the square root of 4 plus x cubed. You want to use Simpson's rule with n equal to 6 to estimate this. Okay. So if you remember Simpson's rule, right? For Simpson's rule, using 6 intervals, it's going to be the b minus a over 3 times n. And then it's going to be 1 times f of your first point plus 4 times f of your next point. And then it's right, it's the 4, 2, 4, 2, 4, 2. And then 4. So part of me feels like this question is meant to address, like, do you remember Simpson's rule? And then 3 times f of x of 4, and then 4 times f of x of 5, and then 1 times f of x of 6. So if there's n equals 6 subintervals, there's 7 endpoints, right? There's the one on the left of the first interval and then the right, and so on and so forth. So I would probably draw a little picture. Like, okay, I know I'm going from 5 to 8. I know it's not to scale. I'm breaking that up into 6 sections. So each section is going to be 1/2 long, right? Delta x, which is b minus a over n, it's going to be 8 minus 5 over 6, which is 3/6, which is 1/2. Okay. So then I'm going to break this up into 6 1/2 long intervals. So I'm going to have 5 and then 5.5 and then 6 and then 6.5 and then 7 and then 7.5 and then 8. And then I'm just going to throw those into the formula. So, right, 5 is my x of 0, 5.5 is my x of 1, x of 2, x of 3, x of 4, x of 5, x of 6. So we just toss it in the formula. So it's going to be, let's see. So we're going to get b minus a, which is 3, over 3 times n, which is 3 times 6, which will reduce to 1/6. And then we would have, again, our function is the square root of 4 plus x cubed. So we'd have 1 times the square root of 4 plus 5 cubed. And then plus 4 times the square root of 4 plus 5.5 cubed. And then 2 times the square root, right? It's kind of a little silly to do this. 2 times the square root of 4 plus 6 cubed plus 4 times the square root of 4 plus 6.5 cubed. 1, 4, 2, 4. Yeah. I feel like I missed one. No, 5, 5.5, 6, 6.5. We're going to get a 2, then 4. Okay, yeah. And plus 2 times the square root of 4 plus 7 cubed plus 4 times the square root of 4 plus 7.5 cubed, and then plus 1 times the square root of 4 plus 8 cubed. Doesn't feel like we really did a whole lot of math there. So like, if this was a test question, which seems somewhat unlikely, but if you had a question like this on the test, I would definitely leave it like that, right? Unless they specifically say get out of calculator, simplify or approximate it. This is where we should leave our answer. Maybe they cancel the 3 here and the 3 here to get a 1/6, but that's kind of it. Let's go ahead and make it a little more interesting. Let's ask ourselves, might as well follow up. What is, that's yeah, maybe not. I was going to ask an error question for this one, but doing an error question here would be kind of gross, taking the derivative of that 4 times. Let's ask a slightly different question. What would the maximum error be if we use the trapezoid method with n equal to 6? Okay. So we know that the error formula using the trapezoid method is that the absolute value of the error is less than or equal to b minus a cubed over 12n squared times the maximum of the absolute value of the second derivative. I mean, most of this is pretty straightforward. B minus a is 3. So we have, right, 8 minus 5. So we have 3 cubed over 12 times 6 squared. We can simplify that in a minute. But then we have this part here, which is kind of a big deal. So let's take this, we can take the maximum, find the maximum of the second derivative. So the function was the square root of 4 plus x cubed. Yeah, square root of 4 plus x cubed. So we're going to get the square root of 4 plus x cubed, or 4 plus x cubed to the 1/2 power. The first derivative is 1/2 times 4 plus x cubed to the negative 1/2 power times 3x squared. So it's going to get a little bit messy. And then the product rule. I think I might write this as a quotient. Yeah. So I'm going to write this as 3x squared over 2 times 4 plus x cubed to the 1/2. And then I'm taking the derivative of that. So the derivative of that's going to be kind of gross. It's going to be the bottom times the derivative of the top, which is 6x, minus the top, which is 3x squared, times the derivative of the bottom, which is going to be 2 times 1/2 is going to be, yeah, it's getting messy. I don't know if I want to do it that way. Sorry. So what happens when you make up problems on your own? Let's come back here. So taking the second derivative, we're going to get, let's just use the product rule. So it's going to be 1 or 3/2 times derivative of this, which is going to be negative 1/2 times 4 plus x cubed to the negative 3/2 times that, plus this. Oh, sorry, I factored out the 3, so I don't have the 3 there anymore. And then plus, so the derivative of this 2x times that, which is 4 plus x cubed to the minus 1/2. Okay, the issue with this, the reason this is challenging is because we're trying to get an upper bound on this, but it's really kind of, right, when you have things added together, it can be kind of really dicey. So here's what I would do. I would factor out the bigger, the smaller power, which is the more negative power of 4 plus x cubed. So I would factor out an x and a 4 plus x cubed to the negative 3/2. So 4 plus x cubed to the negative 3/2. And I also have an x. And I also have this 3/2 out in front. And then left with inside here a negative 1/2 x plus a 2 times 4 plus x cubed. Okay. Yeah, that's kind of gross. So that's going to be, in the denominator, we're going to have a 4 plus x cubed to the 3/2. We also have a 3/2. We have an x, and then we have all of this, which is going to be 2x cubed minus 1/2 x plus 8. And then you have to figure out what the most this can be is on the interval from 5 to 8. So here's where we do the thing where we make the top as big as possible and the bottom as small as possible. So to make the bottom as small as possible, we're going to pick x equal to 5. So we're going to have a denominator of 2 plus 4 plus 5 cubed to the 3/2 power. Well, that's just awful already. And then the numerator, we're going to have, I'm going to put an 8 there, an 8 there, a 5 there, and that's 8. And again, we're going to make the numerator as big as possible on this interval. So I'm going to have 3 times 8. And the biggest this can be is when this x is as large as possible. So 2 times 8 cubed minus when this is as small as possible. Right, if you're subtracting it off to make it big, you want that value to be small. So this might not have been a very good example. I apologize for that. So this terrible looking thing is what would go in here. And then that would be the upper bound of the error. This was a poor example. Sorry about that. I thought it looked like a good function, but it was clearly not a good function. So, right, but the point still remains. When you're trying to find the upper bound on your error, you have to figure out what the maximum of your second derivative is. And if your function ends up being some sort of convoluted looking quotient at the end, you're trying to make the numerator as large as possible, the denominator as small as possible, even if that means picking different values for x to accomplish that goal. All right, let's look at something that's a little less terrible. Well, everybody had an okay 3-day weekend. I know a 3-day weekend right before finals is not probably the most relaxing time to have a 3-day weekend. I'm sure it's still nice, but finals looming over your head makes probably feel like, I need to study. So hopefully you still have to have some relaxing time, even if you were doing some studying. So let's find this integral. The integral of x to the 6 plus 1 times the square root of x to the 7 plus 7x plus 3. Yeah, I think it's a pretty straightforward use substitution. Let's try setting u equal to what makes sense, the insides here. We set u equal to x to the 7th plus 7x plus 3. Our du is going to be 7x to the 6th plus 7 dx. And we essentially have that. Well, I mean, we have that divided by 7. So let's divide this by 7. Divide both sides by 7. So 1/7 du equals x to the 6th plus 1 times dx. And that's exactly what we've got. So here's our, right, that part there is going to be our 1/7 du. So we can rewrite this integral as the integral of 1/7 du. And then that's just going to be the square root of u, or u to the 1/2. And then we know how to integrate that. So your 1/7. The integral of u to the 1/2, you're going to add 1 to the power and get 3/2. And then dividing by 3/2 is the same as multiplying by 2/3. And then plus c. And then we have to plug back in what u is equal to. So I'm going to simplify this as 2/21 times u, which is x to the 7th plus 7x plus 3 to the 3/2 power plus c. That's not too bad. All right. Again, do stop me if you have questions. All right, let's look at this next one here. So it says find dy dx equal to y prime. Someone, sorry, my email is making noise, which is terrible. Well, I'll just deal with that later. Someone's asking if I had office hours today at 9 o'clock, but I don't because it's not Monday. So find dy dx to y prime if we have the equation y times e to the x cubed plus natural log of y plus 3x to the 4th equals 2. So even though they didn't say it, this question is screaming at us to use implicit differentiation, right? You've got x's and y's jumbled together. You have to take the derivative implicitly. Meaning when we differentiate something with y in it, we're going to end up multiplying by y prime. So I'm going to take the derivative of the entire equation. The derivative of y times e to the x cubed. All right, so I'm going to use the product rule. Derivative the first thing, derivative of y is y prime times leave e to the x cubed alone. Plus, then we switch it. We leave the y alone. We multiply by the derivative of e to the x cubed. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So e to the x cubed times 3x squared. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. So the derivative of the natural log of y is 1 over y times the derivative of y. The derivative of 3x to the fourth is just 12x cubed, and the derivative of 2 is 0. So then we need to isolate y prime. So this term here and this term here both have y prime, so they're going to stay on that side, and the other stuff is going to go to the other side. So I have y prime e to the x cubed plus 1 over y times y prime is equal to negative that minus that. So negative y e to the x cubed times 3x squared minus 12x cubed. Then I factor out a y prime. That's why I brought all the y prime things to one side. So factor out a y prime, you're left with e to the x cubed plus 1 over y. Still equal to the same thing. Negative y e to the x cubed times 3x squared minus 12x cubed. And then finally, we're going to divide both sides by this e to the x cubed plus 1 over y. So that y prime is equal to negative y e to the x cubed times 3x squared minus 12x cubed divided by e to the x cubed plus 1 over y. And I would leave it like that. You might see some people simplify this one step to get rid of this fraction of the denominator by multiplying the top and bottom by y, but I don't think that's particularly necessary here. All right, moving along. Again, for those of you that joined us late, we were looking at the sample finals I posted in Canvas earlier this morning. It's at the very top of the module section, so if you want to look at the questions that I'm doing, as opposed to just seeing me right there, you can go to Canvas in the module section and see these sample final exams that I am grabbing problems from. So look at this integral. The integral of x squared divided by the square root of 2x plus 3. So it doesn't feel like we have a whole lot of options here. It feels like, I mean, we definitely can't use integration by parts because we don't have a mixture of things. We can't use partial fractions because the bottom isn't the polynomial. It looks like we'll probably look, I mean, really, before I said any of that, I should ask myself, can I do a U substitution? Because the U sub is usually the first thing we try to do. And we can, but it doesn't feel quite right. So the only real choice for U here is 2x plus 3. Or the only, I should say, the only really plausible choice for U here is 2x plus 3. And the reason that's a plausible choice is because 2x plus 3 is stuck inside the square root. The reason it feels less plausible maybe than usual is because typically we're trying to pick a choice for U so that the derivative of U is also in your function, in your integral. But, right, I mean, it is, right, the derivative of U is a constant, but we would really have preferred, like, you know, it would have been nice if we could have picked U equal to x squared and said the derivative is 2x, but, or really the du is 2x dx, but we don't have a 2x dx, so we can't make that choice. So it just feels a little bit less typical than usual. Our du is 2 dx, so our 1/2 du is dx. So we're going to start replacing things like we usually do. So my dx is 1/2 du. Okay, took care of that. My denominator is the square root of u. Then I have x squared left in the numerator. And to deal with that, we have to do a back substitution. So I'm going to take this choice for u, and I'm going to solve for x. So let's do it down here. U minus 3 equals 2x. U minus 3 times 1/2 equals x. So that's just going to get plugged in for x, and then we're going to square that. So we're going to have 1/2 times u minus 3 quantity squared. That's what's going to happen there. And then we have to multiply it out. This is going to be 1/2 times the integral. 1/2 squared is 1/4. And u minus 3 squared is u squared minus 6u plus 9. All divided by u to the 1/2. I would factor out the 1/4. So 1/2 times 1/4 is 1/8. And then I would divide each of these things by your single denominator. So u squared divided by, in fact, let's just write it out. So if u squared divided by u to the 1/2 minus 6u divided by u to the 1/2 plus 9 divided by u to the 1/2. And then we're going to write those all as powers of u. This is going to be 1/8 times the integral of u to the second divided by u to the 1/2. You're going to subtract those powers and get u to the 3/2. 1 minus 1/2 is 1/2, so you're going to get minus 6u to the 1/2. And then 9 divided by u to the 1/2 is just 9 times u to the negative 1/2. Now we're ready to integrate. So we're going to get, not enough room, so we're going to get 1/8 times u to the 5/2 times 2/5 minus, not enough room, 6u to the 3/2 times 2/3. And finally, plus 9u to the positive 1/2 divided by 1/2 is multiplied by 2. Plus c. And then we're out of room. We still need to plug back in what u is equal to. So let's go. Never enough room. I guess we'll erase the original problem. So we'll say that the integral of x squared divided by the square root of 2x plus 3 dx is equal to, so it's all this, but plugging back in that u is equal to 2x plus 3. So it's going to be 1/8 times 2/5 times 2x plus 3 to the 5/2. And then 6 times 2/3 is going to be 9. All right. Sorry, no. Oh, 6 times 2/3 is going to be, I multiplied 3/2 in my head, not 2/3. 6 times 2/3 is going to be 4. So we're going to get minus 4 times 2x plus 3 to the 3/2. And then we're going to get plus 9 times 2 is 18 times 2x plus 3 to the 1/2 plus c. And that's how you do a problem like that. So if you're not really sure what to do with an integral, but you don't really have a lot of choices, like you don't have a thing that would indicate you could do integration by parts or partial fractions, or another method that I can't remember at the moment. Anyway, if you can't really try any of those things, oftentimes it's a u sub where you just kind of make the only choice that you have available to you, which in this case is you can really, if you're trying to pick u, you're usually trying to pick the thing that is stuck inside another function. How did 1/8 become 1/2? Because I wrote it wrong. Because I made a mistake. Yeah, it should be 1/8 still. Thanks. Now let's see. So to the person who sent me the direct message, that shouldn't be the case. So someone asked, said, I noticed on Lee's homework 8, we didn't change the boundaries when we did u sub. Why is that? We wouldn't change or adjust the interval boundaries for probability when we u sub, but we did just regular definite intervals. Yeah, so usually when you do, I mean, really any u substitution with a definite integral, you either should be changing the limits of integration, or you cannot change them as long if you change the integral back to the original variable you started with. So for the person who sent me that message, if you could, let me take a look here. Is homework 8 still available? I'm just curious what question that is, because that shouldn't be the case really. Let me take a look here. 16B, Lee. Let's see if I can get to the homework. Let's see, I can see it. Okay. See it. Okay, Okay, let me see. Number 12. Okay. Well, okay, I think yeah. Okay, that's a fair question. Here's what's happening with this. So for number 12 on homework 8, for Lee's class, here's what the setup is. The setup is the time t in hours required for a new employee to successfully learn to operate a machine in the manufacturing process is described by the probability function f of t equals kt times the square root of 36 minus t. There's actually a couple things going on here for the person asking the question, but yeah. So the first question is what? On the interval from 0 to 36. You know what? I'm going to change this one because remember I did this one last time. The number 36 was pretty ugly. Let's actually make it. Let's do 4 instead of 36. So be a little bit nicer that way. Still the same idea though. So this first question asks is what is k? Well, we know the integral of this on that interval should equal 1, right? That's the hallmark of being a PDF. So the integral from 0 to 4 of kt times the square root of 4 minus t dt is what we want to find. So we're going to do a u sub here. And our u sub is going to be that u is equal to 4 minus t. Now, yeah, I'm going to do it this way. So then our du is going to be negative dt, and a negative du is positive dt. So if we integrate this, we're going to get, let's see, the integral of k times t. I need to solve for t, right? So I have a negative du. And then square root of 4 minus t is going to be the square root of u. And then this leftover t here, well, if I add t plus u equals 4. So t equals 4 minus u. Now, our limits of integration I'm also going to change. So if u equals 0, if t equals 0, u is going to equal 4 minus 0, which is 4. And if t equals 4, u is going to equal 4 minus 4, which is 0. So limits of integration are from 4 to 0. Now, what I did with this problem the previous time we did it was I then switched these to get rid of this negative sign. So it's not that we didn't change limits of integration, is that when we did the u substitution and we switched them, the limits of integration happened to be the same. That does happen sometimes when you're doing a u substitution. Sometimes you make a u sub and you end up with the same limits of integration you started with. But we did actually change them. So, but I'm actually not going to do that here because of what the rest of the problem is asking us to do. So in this case, it is going to be, I think, somewhat beneficial to leave these as is. In fact, I think I might actually change things back to be, I'm going to change things back to being in terms of x because of what the rest of the question asks us. So we could do this, or we could just kind of pretend they're not there for a minute. I'm going to switch things back to x at the end. So this is going to end up being negative k times the integral of 4 times the square root of u is 4 u to the 1/2. U times the square root of u is u to the 3/2 du. Then we're going to integrate that. We're going to get negative k times, let's see, 4u to the 3/2 times 2/3. So 8/3 u to the 3/2. And then minus 2/5 u to the 5/2. And then I'm going to plug back in that u is equal to 4 minus t. This is going to equal negative k times 8/3 4 minus t to the 3/2 minus 2/5 4 minus t to the 5/2. there is a good reason for doing this. And then I'm going to integrate that from 0 to 4. And then set that equal to 1. Hopefully you guys can all see that when I plug in the 4, I'm going to get 0. Right? 0 here, 0 here. So plugging in the 4, I get 0. And then I'm going to get 0 minus negative k times all this when I plug in 0, which is going to be 8/3 times 4 to the 3/2 minus 2/5 times 4 to the 5/2. That's supposed to equal 1. Okay, so then this is positive k times, let's see, 4 to the 3/2 is 8. 8 times 8/3 is 64/3. And then 4 to the 5/2 is 32. And 2/5 times 32 is 64/5. So k is going to equal 1 divided by that, which is going to be not nice. So 1 divided by 64/3 minus 64/5, which I'm sure we could simplify, but it's not that important. Okay. The reason I wanted to show you this specifically is because the rest of the question asks something like, what's the probability that the time it takes the time it takes for a new employee to learn how the machine works is less than 3 hours. The probability that the time is less than 3 hours. So then I want to find the interval from 0 to 3 of this thing. I'm just going to write it as kt times the square root of 4 minus t, even though I know what k is. Well, the reason I'm writing it this way is because then I can just say, oh, that's going to be this same integral, but instead of going from 0 to 4, I'm going to go from 0 to 3. So that's going to be this thing here, negative k, whatever that is, times 8/3 4 minus t to the 3/2 minus 2/5 4 minus t to the 5/2 from 0 to 3. And then you would plug in 3 for t, and it's going to be kind of awful, right? It's going to be negative k times 8/3 times. Luckily, when you plug in 3, 4 minus 3 is 1, and 1 to any power is 1. So you get negative k times 8/3 minus 2/5 minus negative k times, and then you plug in 0, and you actually get the same thing you got over here, right? When you plug in 0, you get exactly this number right there. So if you use the work you already did, you can sometimes make the rest of it a little bit easier to deal with. I'm plugging in 0, I get 64 minus 64. So yeah, that's not too terrible. Which this part should just be 1 then, right? Because k times this is 1. Interesting. Yeah. So for that helps clarify. No, that's all right. I'm happy to clarify. Yeah, so I think the issue there was mostly not that we didn't change limits of integration, but that when we did change them, they happened to be the same. But I'm happy to answer other questions. Like don't have like my heart set on doing these other problems. They just happen to be good source material. So if you guys have other questions, I'm happy to address them. Let's go ahead and look at this next one. Everyone's doing all right. It's a hot day in Woodland yesterday, to like 160 degrees. It's a little too warm for me. Here's the next one. You wish to invest $100,000 at 7%. I mean, who doesn't wish to invest money at 7% interest? So $100,000 at 7% interest, compounded continuously. how long will it take for the money to accumulate to $350,000? How long until we reach $350,000? Okay, so the compound interest formula is that the amount of money after so much time is equal, the compounded continuously interest formula is the amount of money after some time is the principal times e to the RT, or PERT. So all we're doing here is we want the amount to be 350,000. The principal is 100,000. E to the R is 0.07. And T is what we're trying to solve for. I think that's pretty straightforward. Divide both sides by 100,000, so you ended with 350,000 divided by 100,000. Which simplifies down to 35 over 10 or 7 over 2 or 3.5, whatever you want to call it. That's going to equal e to the 0.07t. Take the natural log of both sides. So I'm going to say this is 3.5. Natural log of 3.5 equals 0.07 times t. And then t is going to equal the natural log of 3.5 divided by 0.07. And that's where you should leave your answer, unless they're giving you decimal or calculators to use. The natural log of 3.5 divided by 0.07 is approximately 17.89. So I would say it's approximately 17.9 years. Okay, it seems not unreasonable for that to take that long. I feel like the sample final here, the questions are definitely not in any particular order. Like it's kind of like just here's a thing, and here's a different thing, and here's another different thing. It doesn't feel very sequential. Let's see. Let's try this one. The integral of x squared minus 3x plus 8 divided by x times x minus 2 squared. And while we could try a u sub here, and it's probably, you probably at least want to think about a u sub, like maybe the top is actually the derivative of the bottom. I don't think it is. I guess we could multiply at the bottom to c. On the bottom, let's see, x minus 2 squared is x squared minus 4x plus 4, and then times x, that would be x cubed minus 4x squared plus 4x. You take the derivative of that, if that was your choice for u, your derivative would be 3x squared minus 8x plus 4. And we don't really have that on top, and it would be really hard to make this equal to that, right? Like you couldn't do it by multiplying or dividing by a constant. If you divided this by 3, you're definitely not going to get x squared minus 3x plus 8. You're going to get x squared minus 8 thirds x plus, right? So not a u-sub problem. Also, it's definitely written in a way that is telling us we should probably try what? What method should we try here, if not u-sub? I know you guys know. Yeah, of course. Right? It's a rational function, and the denominator is already pre-factored for us. It is screaming to use partial fractions. So we're going to have x squared minus 3x plus 8 divided by x times x minus 2 squared equal to, so we're going to have a over x, you're going to have b over this thing, but then since it's a repeated linear factor, or it's a linear factor to a power higher than 1, we have to have all the lower powers as well. So we also need a c over x minus 2. Excuse me. And then we're going to multiply both sides of the equation by our common denominator. So when we do that, we get on the left just x squared minus 3x plus 8. On the right, we get a times x minus 2 squared, because this times this cancels an x. We get b times x, because the x minus 2 squared cancels. And we get c times x minus 2. There's only one of the x minus 2's cancel. And then, if we're going to do it the most efficient way, we start picking convenient values. So one convenient value of x is x equal to 0, because it makes things 0. Or I mean, it makes most of these 0. Plugging in 0 for x, we get 0 minus 0 plus 8 equal to a times negative 2 squared plus b times 0 plus c times 0. So I end up getting a times 4 equals 8. So a equals 2. Great. Okay, what's the other convenient value I can pick for x that's going to make a lot of things equal to 0? X equal to what? Yeah, thanks, Madison. X equal to 2. So now I'm going to substitute in x equal to 2 for both sides. So 2 squared is 4 minus 6 plus 8, that's on the left, equals a times 0 plus b times 2 plus c times 2 times 0. So, right, again, when you're plugging these convenient values, everything on the right side should be 0 except for one of the terms. So then, let's see, 4 minus 6 is negative 2 plus 8 is positive 6. That doesn't seem right. No, it is. Just, yeah. So 2b equals 6, b equals 3. But now we're out of convenient values. This is when we start equating coefficients. And I always suggest starting with the highest power of x. So I'm going to look at the coefficient of x squared. On the left, I have a 1x squared. On the right, if I multiply this out, I would have an a times x squared. I would not have a b times x squared, but I would have a c times x squared. So then I would have 1 has to equal a plus c. But a is equal to 2. So c has to equal negative 1. 1 minus 2. So there's our partial fraction decomposition. And then we have to go back and actually integrate this thing. So we're going to do the integral of a, which is 2 over x, plus b, which is, where'd you go, b? 3 over x minus 2 squared, minus or plus negative 1 or minus 1 over x minus 2. That's what we now have to integrate. So you can, you can show a bunch of work here. I don't think you need to, but let me show you the work I'm not usually showing. So you can break this up into 2 times the integral of 1 over x plus 3 times the integral of 1 over x minus 2 squared minus the integral of 1 over x minus 2. I don't think you need to show that step at all, but it's fine if you want to. Then we can jump straight to, this is 2 times the natural log of the opposite value of x. I'm going to leave this one alone for a minute. And this is going to be minus the natural log of the opposite value of x minus 2. C. So I have this middle part to deal with though. So this here, this is going to be 3 times 1 over x minus 2 squared. It might be helpful to write it as x minus 2 to the negative second. So this one, it's not a logarithm that's our answer. It's just we're going to use the reverse power rule. So we've got something, and since it's 1x minus 2, right? It's not like 3x or 4x. There's no kind of, you could do a u sub here, but you don't really have to. You could let u equal x minus 2. But if you do that, if you let u equal x minus 2, then du is just dx. And so this becomes the integral of u to the minus 2 du. We know how to integrate that. It's just u to the minus 1 divided by minus 1. But then we know how to integrate this. It's just x minus 2 to the minus 1 divided by minus 1. So if your choice for u would just be x plus or minus something, you really can kind of get away without actually doing the u substitution. Just be like, oh, it's essentially u. And I know how to integrate u to the minus 2. I know how to integrate x minus x minus something to the minus 2. All right. Let me go grab more water. I'll be right back. Ran out of water. Okay, I'm back. Let's do more. Now, so this next one. Again, if there are other questions you have you want to see, just let me know. This one says, let R be the region in the XY plane enclosed by the graphs of y equals x cubed minus 2x squared minus 6x and by y equal to 2x. Set up, but do not evaluate an integral formula for the area of the region. Okay, so we need to figure out where these intersect. I don't know exactly what these look like. I have a pretty good idea what they look like, but this is a cubic function, so you don't have to draw this. In fact, let's do it without drawing it, and then I'll kind of come back to it. So to find where these intersect, we need to set them equal to each other. So I'm going to set x cubed minus 2x squared minus 6x equal to 2x. Bring this over, so x cubed minus 2x squared minus 6x minus 2x is minus 8x. 0. And while it might be really, really tempting, you really don't want to divide both sides by x. You want to factor out an x. I'm going to factor out an x, and I'm left with x squared minus 2x minus 8 equal to 0. And I can factor this, that's going to be x minus 4 times x plus 2 equal to 0. So they intersect at x equal to 0, x equal to 4, and x equal to negative 2. Since there's more than 2 points of intersection, we're going to have more than one interval. Basically, every extra point of intersection usually means we have an extra interval to write down. So we have negative 2 to 0 and 0 to 4. And in each of these two intervals, we need to figure out which function is bigger. So you need to pick a point in between there and plug it into both functions and see which one's bigger. So I picked negative 1, and I should give these different names. So I'm going to call this one f of x. I'm going to call this one g of x, because it makes it easier. If I look at f of negative 1, that's going to be negative 1 cubed, which is negative 1, minus 2 times negative 1 squared, which is going to be minus 2, because negative 1 squared is still positive 1, and negative 2 times 1 is negative 2. And then minus 6 times negative 1 is plus 6. So you get minus 3 plus 6, which is 3. And g of negative 1 is going to be 2 times negative 1, which is just negative 2. So f is bigger on this interval. So from here to here, f is bigger than g. It could also be true that f is bigger than g over here. We need to check. Sometimes they don't actually cross each other. So let's plug in x equal to 1. So f of 1 is going to be 1 minus 2 minus 6, which is going to be, let's see, negative 7. And g of 1 is going to be 2 times 1, which is 2. So in this interval, between 0 and 4, g is bigger. And whenever you're finding the area between two curves on an interval, you're always doing the integral of the larger function minus the smaller function. So to set this up, we're going to say that the area is equal to the integral from negative 2 to 0 of the bigger function minus the smaller function, so f minus g. That's going to be x cubed minus 2x squared minus 6x minus 2x dx. Or you could even put those together and write it as minus 8x. Like that would be fine, right? You'd have essentially this. And then plus the integral from 0 to 4 of g minus f. That's going to be 2x minus x cubed minus 2x squared minus 6x. Good tip to know, if you're doing something like this and you do have them subtracted in the opposite order, you could make your life easier. And so if you want to make your life easier, you say, okay, well, I know f minus g, right? This f minus g here, if I simplified it, that would be x cubed minus 2x squared minus 8x. And then if I'm doing g minus f, it should exactly be the negative of f minus g. So you can say, oh, that's going to be negative x cubed plus 2x squared plus 8x. Just looking at f minus g and making every time the opposite of what it was. So that can save you a little bit of work if you're actually trying to having to do the integral. So you want to simplify this stuff inside the integral first. But yeah, if you didn't have to do the integral, then just leave it like that. So definitely don't draw a picture for this. You just need to find the place where they intersect. And then for each interval between 2 points of intersection, you have to determine which function is larger and which function is smaller. All right, let's look at the next one. So an experiment has found that bacteria grow at a rate of 3% per hour. So bacteria grow at 3% per hour. If there are 10,000 bacteria after 15 hours, so we have 10,000 bacteria after 13 hours. How many bacteria are present at the beginning of the experiment? Okay. And so this problem, I believe, is slightly trickier than you might think, in that, yeah. Sorry. I believe you're supposed to do this one, and again, I don't know the intent of the writer of this problem. Right, if the bacteria grow at 3% per hour, that doesn't mean that your R is 3%. So, right, it would be incorrect to say that we have like y equals CE to the 0.03, sorry, yeah, no, 0.03t. That would not be exactly right. Because after 1 hour, you're not actually going to grow by 3% this way. Right, let's pretend we started with C equals, let's say we started with 100 bacteria. So at times 0, you have 100 this way. Then if you plug in T equal to 1, so you get 0.03, e to the 0.03 times 100 is, it's going to be close. It's going to be real close, actually. It is very close, but it's not exactly 3%. You get 103.045453. So the point of a problem like this usually, and so I should be careful here, right? Usually they will say very specifically if they want you to let your R value be, or your K value be 0.03. Here, I believe the intent is to say, well, I know that I actually don't know anything really, right? I know that at time equal to 0, my amount of stuff is what I'm actually trying to find. And I know that 15 hours later, I have 10,000. I also know that 1 hour later, I should have 3% more. I should have 1.03 times whatever I started with, because that's 3% more. So what I'm going to do is I'm actually going to use that and say, okay, well, I know that when I plug in time equal to 1, on the right-hand side, I have c times e to the k times 1. On the left-hand side, I'm going to have 3% more than I started with, so 1.03 times c. I can divide both sides by c. And I can take the natural log of both sides. Natural log of 1.03 is k. And I will tell you, natural log of 1.03 is very, very close to actually just being 0.03. I can tell you, in fact, it's about 0.0295588. So right, very close to 0.03. But not exactly the same. So it does matter. So there's our k value. And so now here's what we've got. We've got y equal to c e to the natural log of 1.03 times t. And then we can use our other piece of data to figure out what the initial value must have been. So I plug in 10,000 for y and 15 for t. We can solve for c. So it looks like c is going to equal 10,000 divided by e to the natural log of 1.03 times 15. Whatever that number is. I don't think we actually need to find it. Oh, fine, we can find it. Let's see. So that's going to be approximately 6,418 bacteria. Okay. You might know this better. In fact, it might make more sense to you to think of this. This is the same as y equals c times 1.03 to the t power. It's another way of writing this. That might make it more obvious that, oh yeah, we're growing at 3% every hour, because every time t increases by 1, you're multiplying by another 1.03. All right. Long. All right, we got 10. Okay. So let's see. Find the derivative of the following. So find dy dx. Given that y is equal to 5 to the natural log of x squared plus 2. That seems x squared plus 3, sorry. It seems a little too easy, personally. So there's two ways you can approach this. Since your base is a constant, right? We know that the derivative is going to be, I forget which way your professors like to do this. The way I remember to do this is that, right, the derivative of, so I know the derivative of e to the x is e to the x. The derivative of a to the x is a to the x times the natural log of a. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. And the derivative of a to the stuff is a to the stuff times the derivative of the stuff times the natural log of a. So that's what I'm thinking of when I see this. Since my base is a constant, right, I can just say that the derivative is going to be, okay, the derivative of a to the stuff is a to the stuff times the derivative of that exponent, which is going to be the derivative of the natural log of x squared plus 3, is 1 over x squared plus 3 times 2x, right? 1 over the stuff times the derivative of the stuff, and then times the natural log of 5. That'd be perfectly fine. Or the other way people do this problem, which is also perfectly legit, is to say, well, y is equal to, instead of writing it as 5 to the natural log of x squared plus 3, you can say it's e to the natural log of 5 to the natural log of x squared plus 3. And then you can bring down this power right there. And so you've got y equal to e to the natural log of x squared plus 3 times the natural log of 5. And then we know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So our derivative here is going to be, e to the stuff is e to the same stuff times the derivative of that stuff. Now the derivative of this stuff, I have natural log of x squared plus 3 times natural log of 5. I don't need to use the product rule because natural log of 5 is just a constant. So the derivative, the natural log of x squared plus 3 times natural log of 5 is just the derivative of the natural log of x squared plus 3, which is 1 over x squared plus 3 times 2x. And then the natural log of 5 constant multiple just hangs out. Well, look, this is exactly the same as that because this is exactly the same as that. So the same. This question does get more interesting, more challenging if our base is no longer a constant. Let's look at that. Let's say we had the same problem, in fact, except that now instead of 5, our base is x. So let's find the derivative of x to the natural log of x squared plus 3. Now this sort of problem, and you certainly could have done this for the previous one, but for this one, you really have to use the process of logarithmic differentiation. So I'm going to say y equals x to the natural log of x squared plus 3, and then take the natural log of both sides. So the natural log of y equals the natural log of x to the natural log of x squared plus 3. And then bring this power down. So the natural log of y equals the natural log of x squared plus 3 times the natural log of x. And now we differentiate both sides. And here we are going to have to use the product rule when we differentiate that side. So here you get the derivative of the natural log of y is 1 over y times y prime. Right, 1 over the stuff times the derivative of the stuff. And then on the right hand side, product rule. So the derivative of the natural log of x squared plus 3 is 1 over x squared plus 3 times 2x, and then times the other function, plus, then we flip it. We leave this one alone. We multiply by the derivative of that, which is just 1 over x. Finally, we have to multiply both sides by y. And let's simplify as we do that. So y prime equals y times, let's say this is 2x natural log of x over x squared plus 3. And this is the natural log of x squared plus 3 divided by x. And then finally, y is equal to that. So this is y prime is equal to x to the natural log of x squared plus 3 times all this. 2x natural log of x over x squared plus 3 plus natural log of x squared plus 3 divided by x. Whew. All right. All right, let's do this next one. This next one might take a moment. The region R in the first quadrant, and they drew it for us a little bit too. So we've got the region R in the first quadrant is bounded by the graph of y equals secant x, and bounded below, bounded above by the graph of y equals secant x, bounded below by the graph of f of y equal e to the negative x, and bounded on the right by the line x equals pi over 3. And they've given us what it looks like. So here's vaguely what secant looks like from 0 to pi over 3. Here's the vertical line, x equals pi over 3. And here's y equals e to the negative x. We actually don't really know this a little bit there. Okay. And we are being asked to revolve the region around the x-axis and find the volume of the solid we get. So we're definitely using the washer method here because the axis of rotation is not one of our boundaries. Or in other words, the region is not flush with the axis of rotation. All right, here's our region. There's definitely space between our region and the axis of rotation. So we did the washer method. So we're going to draw, a little vertical strip. And then we're going to talk about what happens with that strip as you rotate it around. So there's our washer. We want to find the volume of our washer. Okay, well, the volume of a washer is always the area of the big circle minus the area of the little circle, all times the thickness of the washer, which is dx, if you're doing it around the x-axis. Or more generally, if you're using a vertical strip. So, our larger radius is the function that's further away from the axis of rotation. In this case, that's going to be secant of x. So this is going to be pi. Let's factor out the pi. Times secant of x quantity squared, or I would write it as, let's write it as secant of x quantity squared minus the smaller radius squared, which is e to the negative x squared. So then the actual volume is going to be the integral from as far left as 0, as far right as pi over 3 of pi times, now let's simplify this. This is going to be secant squared x minus e to the negative x squared is e to the negative 2x. Okay, that's not as awful as it could be. So the pi factors out. The antiderivative of secant squared is tangent. The antiderivative of e to the negative 2x is e to the negative 2x divided by negative 2 from 0 to pi over 3. So plugging in our limits of integration, we're going to get pi times tangent of pi over 3 minus the minus is plus e to the negative 2 pi over 3 over 2 minus, we plug in 0. Tangent of 0 is 0. And e to 0 is 1. So you get minus minus a plus 1. And you can probably leave it like that. I suppose, I take it back a little bit. I would imagine most people would expect you to evaluate tangent of pi over 3. Tangent of pi over 3 is the square root of 3. This is going to be pi times square root of 3 plus e to the negative 2 pi over 3, and then minus 1/2. That would be, that's probably as much work as I would want to do on that problem. All right, let's go to the next one. This next problem is meant to be very easy. In fact, I want everybody to type in the chat. I'll make it private. Everyone can just message me privately. Change that setting real quick here. Let's change it for a minute. All right. Everyone can chat with only me. I'm all you've got. All right, and I want answers. So can find the mean mu of the probability density function f of x equal to, what have we got here? 4/9 times e to the negative 4/9 x on the interval from 0 to infinity. everybody should be able to look at this PDF, this special probability function, and tell me what the mean is without doing any computation. So if you think you know or you have a guess, chat it to me right now. It's okay to be wrong. No one else is going to see your answer except for me. You guess all kinds of crazy things. Or no one could guess anything at all. That would also be an option, I suppose. Okay, fine. So the thing here, you guys, okay, good. Yeah, those are some good guesses. Those are the guesses I expected to see. So someone guessed 4/9 and someone guessed 9/4, and one of those is right, and one of those is wrong. Which is okay to be wrong. So it's actually 9/4. So the mean is 9/4, and the standard deviation is also 9/4. I'll just remind you guys that more generally, if you have an exponential probability density function, right? The what is it? 1 over a times e to the negative 1 over a. I think that's how they write it in the book. No, I'm not sure. 1 over x. Let me double check just to make sure I'm following the book format here. 1 second. Sorry. I'll make sure I'm not getting it. It doesn't really matter, but I would like to do it so it's not confusing to you guys. Right, that would be the better way to do it. No, they don't write it that way in the book. Sorry. The book, they do write it as a times e to the negative ax on the interval from 0 to infinity. If that's your special probability function, then you automatically get to know that the mean and the standard deviation are both equal to 1 over a, or the reciprocal of that coefficient. So seeing that we had a 4/9 out here, we automatically knew that the mean was the reciprocal of that, which is 9/4. Yeah. Let's find the median. So the median is not something I would expect you to remember for this one. And it's not written in the book. I know I told it to you guys last week, but again, I wouldn't expect. I remember what it is. I think it's 9/4 natural log of 2. I'm not positive. But let's talk about how you tell that. Right, to find the median, you want the area to equal 1/2. So right, so you know on your whole interval, this is what your function looks like, and all that area is 1. That's the point of being a probability density function, is the area under the curve over your entire interval is equal to 1. We want to find the place where the area on either side is 1/2. So you could unwisely do the integral from m to infinity and have to deal with an improper integral, or and set that equal to 1/2. Or you could smartly do the integral from 0 to m, set that equal to 1/2. So we're going to do the integral from 0 to m of 4/9 e to the negative 4/9 x. And we're going to set that equal to 1/2, and we're going to solve for m. So let's see. So when you integrate 4/9 e to the negative 4/9 x, you get negative e to the negative 4/9 x. Because if you differentiate this, you end up multiplying by a negative 4/9, which gives you the positive 4/9 right there. And let's see, plugging in our limits of integration, you're going to get negative e to the negative 4/9 m minus negative e to the 0, so plus 1 equals 1/2. Subtract 1 and flip the sign. So instead of having negative this equal to negative 1/2, you'll have positive this equal to positive 1/2. Yeah, that's fine. So e to the negative 4/9 m equals positive 1/2. Take the natural log of both sides. Natural log of e to the negative 4/9 m equals the natural log of 1/2. That's the negative 4/9 m equals natural log of 1/2. But the natural log of 1/2 is really the negative natural log of 2, or you can even think of this as the natural log of 1 minus the natural log of 2, and then that's 0. So then positive 4/9 m equals positive natural log of 2, and m equals 9/4 times the natural log of 2. So yeah. Again, that calculation isn't as terrible as actually, right? Because if you want to calculate the mean or the variance here, you have to do the interval from 0 to infinity, and you have to do improper. And improper can be kind of a bit of a pain in the butt.